power circuits are made up of 5 main components: current sources, voltage sources, resistors, inductors, and capacitors. These are further divided into active and passive components. Starting with the active components, these are current sources and voltage sources. Current sources provide current flow in a circuit, and their representation usually looks like this. An ideal current source is one where the current supplied to it by the load is independent of the voltage across its terminals. The time domain representation of the sinusoidal current signal this source produces is denoted I of t is equal to Im cosine omega t plus phi. Its phasor counterpart is as follows: I is equal to Im e to the j phi. Voltage sources create a voltage drop in a circuit, and their representation in circuit diagrams usually looks like this. An ideal voltage source is one where the drop across the terminals is independent of the current supplied by it to the load. The time domain representation of the sinusoidal voltage signal this source produces is denoted V of t is equal to Vm cosine omega t plus phi. Its phasor counterpart is as follows: V equals Vm e to the j phi. Now moving on to passive components, which either dissipate or store energy. Resistors are circuit elements that do the former, opposing current flow and generating some voltage drop in the process. Their representation in circuit diagrams usually looks like this. The time domain equation of the current flowing through a resistor is I of t equals Im cosine omega t plus phi, and its corresponding phasor is I equals Im e to the j phi. To find the equation for the voltage over time across a resistor, we use Ohm's law. That is, the voltage between 2 points is equal to the current flow between those points, multiplied by the resistance. As we know the resistance R, we simply multiply this with our above equation for current. This gives us V of t equals R Im cosine omega t plus phi. We do the exact same process to find the voltage phasor. V equals Rim e to the j phi. We can map these phasors as vectors in the complex plane. Note that they have the exact same angle phi. Our next type of passive circuit element is the inductor. These store energy in a magnetic field when current flows through them, and they usually take the form of a long spool of wire. Their representation in circuit diagrams usually looks like this. The time domain equation of the current flowing through an inductor is I of t equals Im cosine omega t plus phi, and its corresponding phasor is I equals Im e to the j phi. We find the equation for the voltage across the terminals of an inductor by noting that it is equal to the inductance L multiplied by the rate of change of the current through the inductor. We therefore differentiate our current equation, then rewrite it as a cosine. V of t equals omega Lim cosine omega t plus phi plus 90 degrees. Now we can more easily find our phasor representation. Note here this 90-degree phase shift. As we touched on in our discussion of phasors, to change the phase angle of a signal by 90 degrees in the phasor domain means multiplying by e to the j90. If we plug 90 degrees into Euler's formula, we can see that this is the same as multiplying by the complex number j. Therefore, our phasor for the voltage is V equals j omega L Im to the ej phi. Mapping these current and voltage phasors as vectors in the complex plane, we can see that the voltage of an inductor leads the current by 90 degrees. Recall that these phasors are rotating anticlockwise. Our final type of passive circuit element is the capacitor. These store charge and can be pictured as comprised of 2 plates at different potentials adjacent to each other. Their representation in circuit diagrams usually looks like this. This time, we'll start by finding the time domain equation of the voltage across a capacitor. This is simply V of t equals Vm cosine omega t plus phi, with its corresponding phasor V equals Vm e to the j phi. Now finding the time domain equation of the current through a capacitor. This is equal to the capacitance C multiplied by the rate of change of the voltage across the capacitor. We therefore differentiate our voltage equation, then rewrite it as a cosine. I of t equals omega c Vm cosine omega t plus phi plus 90 degrees. Noting the same 90-degree phase shift, we again multiply our phasor by j to get I equals j omega c Vm e to the j phi. Mapping these current and voltage phasors as vectors in the complex plane, we can see that the current in a capacitor leads the voltage by 90 degrees.